Hello, my name is Gregory Jacob, and today I'll be talking about our optical head using the planar light valve for high throughput and high resolution laser processing. And this is a talk that was given at the Laser Precision Microfabrication Conference in June 11th in 2024. So Silicon Light Machines has been making high-speed spatial light modulators with exceptional power handling capabilities for over 30 years now. This technology has been utilized in many high-throughput printing applications to take advantage of high-power lasers while also maintaining very good resolution. This slide shows two examples of that. On the left is a maskless lithography machine to process 2.5 micron features on the 300 millimeter wafers here. And on the right is a computer-to-plate printing machine that can print these 1 meter tall plates at a rate of about 1 per minute. So as higher energy and higher average power lasers become available, we'd like to take advantage of them to get higher throughput. But single spot systems have some limitations in the fluence that they can deliver to the sample. And so they need to scan very, very quickly to take advantage of high laser powers. As you can see from this graph on the right, to use a 10 micron spot, we can only utilize up to a 50 watt laser when we're using a very high speed polygon scanner. So most of these high power lasers are limited to larger feature sizes and lower resolution applications. So when a customer has an application that requires high resolution, if they need to reach a desired throughput, they might just duplicate the single spot system many times over, but this is costly and can have a large footprint. So SLM has developed an optical head which enables easily creating a multi-spot line beam for high resolution and high throughput applications. At the heart of the optical head is our planar light valve spatial light modulator. And this is our highest power handling spatial light modulator and can be used with pulsed and CW lasers and has a high switching speed of over 100 kilohertz. What the spatial light modulator allows us to do is change the multi-spot pattern on the fly while we're scanning to process our sample. And here's some more information about the planar light valve. It's a MEMS diffractive amplitude modulator. It works over a wide wavelength range, has a switching rate of over 100 kilohertz and a damage threshold of about 20 millijoules per square centimeter, but depends on the wavelength and the pulse width. And you can see the top view of the LPLV on the left-hand side. The orange elements are the face plates, which move up and down, and those are the dynamic part. And they're surrounded by an equal area of the static part to create the interference that we need for diffraction. If you look from the side view, you can see what happens when we pull down those dynamic elements. We create a diffraction grating, and we get the most light going into the higher orders when we have a quarter wavelength of displacement of those dynamic parts. And just above that is an example of an optical system and how we would put a spatial filter at a certain place to block the first orders and higher orders and only allow the modulated 0th order to go through, which gives us the modulation in the output image. This is what the actual MEMS chip looks like. And you can see the active area in the center is the 27 millimeter by 1 millimeter rectangle. And this has 1088 programmable pixels in the x-axis, and each one of those is a column of 40 diffractive MEMS elements in the y-axis, which are ganged together so they move in unison with the same voltage applied to all of them. Zooming in a little bit, you can see one column here is one device pixel. And the reason that we tile so many elements together so that we can have a large area for large power handling. And zooming in further, you can see the individual 25.5 micron square elements with the circular faceplates in the center. And the diffraction orders can be calculated with the grading equation to the right-hand side. Now I'll go over a high-level overview of what the optical head optics layout looks like. So we have an integrated 100-watt 10 picosecond laser, but we've also used the system with an input window so that the user can input a different laser that might better suit their application. Between the laser and the PLV, we have beam shaping optics, which convert the Gaussian beam into a 27 by 1 millimeter top hat by top hat illumination for the PLV. And then after the PLV, we have projection and relay optics, which create a demagnified image on the media. And we also have a pickoff there for the calibration system, which can be used to flatten out any non-uniformities that come from the illumination optics. So in this system, we also have kind of a unique galvo relay system, which both images and scans the beam at the output. A shorter focal length was chosen here of 65 millimeters to maintain high resolution and give 10 micron spot sizes. So the resulting processing field of view with the galvos is 15 by 15 millimeters. So at the output of the optical head, we get a line beam with these segments that can be turned on and off and create arbitrary patterns. This is a video that was taken with the calibration camera, and you can see that any pattern can be put on the PLV to create a different output in the image plane. And this is slowed down, of course, so that we can see it with our eyes, but the switching speed is up over 100 kilohertz. And in this system, we group 4 PLV pixels together to create a 10 micron feature size, which gives us somewhere around 270 different segments that we can turn on and off. Now, to use this in laser processing, we have modulation in the PLV axis, and we just need to scan the beam in the orthogonal axis while changing the pattern to deposit energy where we need it. And if the image is larger than the width of a single line beam, then we scan over multiple times, like the animation on the right is showing. The scanning can be done by moving either the beam or the media. So here's some examples. I'll show some demonstrations shortly of our demo system, which uses XY stages and the galvo mirrors. But there's many ways that scanning the beam and the media can be achieved to give full coverage of the media that we're processing. And these can be used in conjunction with one another. And just a couple of examples are shown here. So first I'll show a demonstration of black marking on stainless steel. And this is going to be scanning the sample with the XY stages. Here you can see it scanning in the serpentine path. And after 5 passes, it's completed. This is what the resulting text looks like. You can see these characters are under 1 millimeter tall, and we get very nice, sharp, and crisp text at the output. And this block was done in under 5 seconds total. Now, this will be a larger image, about 68 by 45 millimeters, and kind of going back to our printing heritage, recreating a photograph on the stainless steel. So this whole print was done in about 36 seconds, and it's the Golden Palace in Kyoto. I'll show some more zoomed in photos later so you can see what the individual dots look like for a dithered image like this. And finally, here's a demonstration using the full 15 by 15 millimeter field of the galvos. So this is a QR code that's printed in just over 2 seconds. Now, when we use the galvos in this system, we are introducing distortion by scanning through the f-theta lens. And you can see that our ideal scan paths become these curved scan paths that you can see on the right side. So typically, these scan paths are corrected with a correction in the Galvo controller. But with our aligned beam, we introduce a little bit more complexity because different points on the beam will have different amounts of distortion. So we can't correct them with a single distortion correction factor in the Galvo controller. So what we did was our approach to correcting the distortion, we marked an array of dots and calculated their displacement from the ideal position. So this is the distortion data that we collected. And then knowing that when we put in a square image, we get the distorted image out, the idea is to pre-distort the image in software so that we can get a square image as a result. So after applying this distortion correction, we marked the grid of dots again, and you can see that the distortion was reduced by about 2.2x. The maximum distortion was brought down to 120 microns, and the average distortion brought down to 33 microns. But there's still some refinement that can be done to get those numbers even lower. And another view of this, you can see we have an original uncorrected image on the left, and then the corrected image in the center and on the right. So this gap between the original and the corrected is it varies by about 68 microns because the original image has some curvature to it. But between the corrected image, the gap only ranges by about 9 microns. So that was reduced by about 7x. Now I'll talk about the resolution and throughput capabilities of our system. So in order to create different size spots in the modulated axis, which is the horizontal axis in these pictures, we group different number of LPLV pixels together. So as we group fewer and fewer pixels together, we get a smaller feature size, and we get well-resolved spots down to the 10 micron feature size that comes from grouping 4 pixels together. If we try to go lower than that, down to 3 pixels, then the contrast of our optics has trouble keeping up with such small feature sizes, and we get lower contrast spots at the output. We also marked some vertical and horizontal line pairs at different scanning speeds. So first you can see the 10 micron lines here that were scanned at 122 millimeters per second. And now we've increased the scan speed up to 854 millimeters per second, and we still get perfectly well resolved vertical lines from our 4 on 4 off pattern. They are a little bit thicker here because I had to mark over them in 10 passes to create the darkness that you see here, but they're still very well resolved. The challenge comes when we want to mark the horizontal lines at higher and higher scan speeds, which corresponds to higher switching speeds of our LPLV modulator. So at a certain point, we start to see the lines become thin and lower contrast, and that happens somewhere around 150 kilohertz. So we saw good switching speeds up to about 117 kilohertz, and then somewhere between 117 and 150 kilohertz, the device is not getting to the full on state before it's switched back to the off state. Now, another important characteristic that goes with the resolution is the edge placement. So we have that minimum feature size of 10 microns, but we can shift that along the PLV axis by a single pixel of 2.5, corresponding to 2.5 microns in the image plane. And that's how we can create very smooth diagonal features, like you can see in the animation here. And here's a real test where I use different grid sizes from 20 microns down to 2.5 microns to create this character. And you can see at the coarser grid sizes, we get a little bit of a staircase effect. And as we go down to the 2.5 micron grid size, the lines become very, very smooth. The only penalty for this is that we need to generate more data and send more data to the device. But At our typical scanning speeds for black marking, the switching speed is under 20 kilohertz, so the device has no problem handling this. But all of these are processed in the exact same time. Now we wanted to characterize the throughput of our system against kind of a typical single spot system using a 50-watt 3 picosecond laser. So to do that, we picked an array of images that you can see here. Some of them have very dense features, which favors our line beam system, but some of them have very sparse features, like this array of dots and the logo here, which should favor the single spot system. And here are the processing time results. The L stars were dialed in to be pretty close to each other. This is the darkness of the black marks to make it a fair comparison. And when you have two samples side by side, if the L star is less than 2, the difference less than 2, it's very hard to tell them apart. So these samples look very similar, but the samples from our line beam system looked much sharper, especially in the text image here. And you can see the throughput enhancement at the minimum was 9.9 for this very sparse image number 2. But for the QR code image number 3, we saw a 35x enhancement in throughput. Now here's just a couple more black marked images on stainless steel. You can see this night piece on the chessboard has a border of 10 microns around it, which is unmarked. And here's another grayscale image, which is created in kind of a dot matrix fashion. And as we zoom in, you can see the individual 10 micron dots, and the density of those dots is what's creating the grayscale effect in these images. And just a couple more sample images here. You can see we can do large, fully black areas, as well as create some cool visual effects like the pyramids in the bottom left. And now I'll quickly touch on some other applications that we've been exploring for this optical head. The first of those is engraving on stainless steel. So this is a 10 millimeter engraved circle here with a depth of about 100 microns. And you can see the steepness of the edge there. And we've gone down to almost 500 micron depth in the sample with removal rates around 1.8 to 2 cubic millimeters per minute. And we can recreate very fine features while engraving also. Something interesting was that after engraving, the bottom surface was quite rough and had a black marked appearance to it. So we played around with doing some high-speed polishing passes to give it a look of more of the bare metal appearance. So the second and third images here use 10 and 100 polishing passes to give a more of the raw stainless steel look to the final image there. And here's a video from a collaboration done with Coherent using their 150 watt 300 femtosecond Monaco laser, just to show how high power femtosecond laser can be used for higher throughput. And finally, here's a wafer marking that was done in collaboration with Andreas Brand at Fraunhofer. And you can see that we get very similar contrast and resolution results to what we saw on the stainless steel. So yeah, some very nice images marked on a silicon wafer here. So to conclude, we've demonstrated our multi-spot optical head with up to a 35x throughput enhancement at much higher resolution compared to a typical single spot system. And we showed using up to 150 watt, but we can use even higher power and higher energy lasers coupled in through input window. And our system has been used with CW down to femtosecond lasers. So this can be adapted for other materials and other processes than were shown here, such as additive manufacturing and lithography. and can be used on metals and plastics and graphite. So in the future, we're continuing to engage customers and seek out new applications for this infrared version of the optical head that was shown today. And we're also developing versions with longer line lengths at the output for even higher throughput, and developing versions at different wavelengths, such as in the green and the UV, to address more potential applications.